Okay, we are going to give another lower bound on the extremal number for KST. Last time we gave a probabilistic bound. This is going to be a simple, straightforward counting bound. It'll resemble the other one. Okay, so here's the theorem. Let's, again, fix t is at least s is at least 2, and then the extremal number for the complete bipartite graph, KST, is at most, let me pull up the bound to get it exactly right here, 1/4 s factorial t factorial all to the 1 over st. This is just a constant term as far as n is concerned, so this is not really what's important. What's important is this part here. So times n to the 2 minus 1 over s minus 1 over t, okay? If you compare that to the bound we had last time in the probabilistic proof, this exponent is a little bit worse. This is a worse upper, by the way, this is a lower bound, not an upper bound, excuse me. It's totally backwards. We're giving a lower bound, right, in construction. So this exponent's not quite as big as the other exponent, although if you fiddle around with s and t, you'll see that they're comparable. They're pretty close, okay? But this is just a totally different proof that I want to present here, okay? So what we're going to do here is we're going to count the total number of graphs on E edges, and then we're going to count the total number of graphs on E edges that have a KST. And if we can show there's a gap between those two numbers, then there are some KST-free graphs, okay? And so solving that's going to require us to manipulate E, the number of edges, and we're going to find that E has to be at least this quantity here in order for it to make it work, okay? So let's count all n vertex E edge graphs. Okay, so the total number of graphs on n vertices with n edges, all right? And I'm even going to put here labeled, because technically these are, the way we're counting these are as labeled graphs. It's not going to make a difference though. All we need to prove is that there exists one labeled graph. If there exists a labeled graph, then there exists a graph without thinking about labelings, okay? Okay, so how do we do that? Well, first of all, the easy count is the number of such things is just simply, well, you have n choose 2 pairs, right? Those are your candidates for edges, n choose 2 pairs, and E of them are going to be edges because you have an E edge graph. So n choose 2 pairs, choose E of them to be edges. So the quantity is exactly that amount there. That's all of them. Okay, so now I'm going to count all n vertex graphs with E edges and a copy of KST as a subgraph, okay? And I'm going to give an upper estimate for this quantity here, okay? So similar to in the probabilistic proof, how do we count the number of graphs, or in that case, predict the probability of such a graph occurring? Well, okay, on the n vertices, S of them I'm going to allow to be one class of the KST, and T of them are going to be the class of size T. Right, so this is already an upper estimate because this technically should be n minus s, but for counting reasons it's just simpler to put n choose t there. Okay, so I've assigned s vertices and t vertices, and all the edges are going to be present here. Right, so I've assigned s times t of the total edges of E. So of the remaining vertices in the graph, I still need to assign E minus s times t edges. Okay, and how do we do that? Well, of the remaining n choose 2 pairs of vertices minus st of them are already spoken for, these st pairs. I need to assign E minus st more edges to fill out the graph there. Okay, so that's the number of graphs with a KST, right? I pre-assign the KST in one of these many ways, and then assign the remaining edges here. This is an upper bound count. Okay, and so what do I have to do here? Well, this is an upper bound on the number of graphs with a KST. This is exactly the value of the number of graphs. So if I can show that this quantity here is strictly less than this quantity here for some E, then there exist graphs that have no KST. Okay, we're not going to actually produce one. Again, we're going to show they exist. So similar to the probabilistic argument. Okay. Okay, so what is my goal here? I want to find E in terms of n such that this guy is less than this guy. So I'll just write that n choose s times n choose t, n choose 2 minus st, e minus st is less than n choose 2 choose e. Those with a KST less than those in total. That means there exists some without a KST. Okay? It's actually the same exact style of reasoning we do in probabilistic proofs. Okay, so in principle, you could actually just expand everything and try and solve for e and find a bound. Oh, e has to be at most whatever, or e has to be greater than or equal to whatever to make it work. But that's difficult to do, so what we're going to do is replace these things with different values. I'm going to replace this with something larger. If something larger than this is still less than this guy here, then this equality follows from it there, okay? So at this point, it's basically just mostly substitutions and some symbol manipulation here. Okay, so I'm just going to work this guy here in order to replace it with something that I still want to be smaller than that. So this will follow from a stronger inequality. Okay, so let's replace this guy with n to the s plus t over s factorial t factorial. Right, that beats this guy. That's something larger than this guy. And then, so I'm writing an inequality here that implies the above inequality. Okay, so this is a little bit backward style of reasoning, but nonetheless, this will work out. And I'm going to move this guy over to this side here. So I have this binomial coefficient. Well, let me write it out here. So n choose 2, choose e, divided by n choose 2 minus st, e minus st. Okay? So if I'm going to prove in this inequality, I get the one above here because I've replaced this with something larger. Okay, and just move this over here. Now this guy here, this is just two binomial coefficients that resemble each other here. If you write out the terms of this and write out the terms of this, many things are going to cancel with each other, right? This n minus, this will be n choose 2 minus 1, n choose 2 minus 3, blah, blah, blah. It'll cancel out with the later terms of this guy here. So I'm going to rewrite this guy here. This can be rewritten as, so the right-hand side here can be rewritten as n choose 2 minus 1, all the way down to n choose 2 minus st plus 1. Plus 1. All the terms after this guy in the top factorial will cancel with the terms of that top factorial. Something similar will happen on the bottom, and we'll be left with e minus 1, all the way down to e minus st plus 1. Okay? So what I'd like to show is that this is strictly less than this, which is this guy here. Okay? Or what I can do instead is show that this is less than something that's smaller than this. If this is smaller than something smaller than this, then this is smaller than this. Okay, so I'm interested in something that's below this. And this is an exercise to prove this inequality here, homework. But this is less than n choose 2 over e, all raised to the st. Okay? Why does that at least make some sense that this is related to this? Well, look at this guy here. There are s times t many terms up top, and s times t many terms up, on the bottom there. The biggest term on top is n choose 2, and the biggest term on bottom is e. If you just replace each of these smaller terms with the biggest here, and replace each of these with the biggest here, and raise it to st for the number of terms, this is actually strictly less than this. Now that's not immediately clear, right? If I replaced all the bottom terms with this term, and all the top terms with this term, this would be clearly, this would clearly be larger. Did I get it backwards? No, yeah. But what I'm doing here is replacing the top, the biggest one here and the biggest one here in these two here. And this happens to be smaller. This is a homework, okay? It's not immediate that that happens. So what I want is the following, this inequality. N to the s plus t over s factorial, t factorial. If this thing holds, if this inequality holds, then it implies this inequality, which says that there's a KST-free graph on n vertices and e edges. So all I need to do is solve this guy for e. Okay, and so what I'm going to do actually is do one final replacement here, and that it's going to follow from this is, hopefully this will be visible at the bottom, but n to the s plus t over s factorial, t factorial, less than, and I'm going to replace n choose 2 with something smaller, so again I get a stronger inequality, and the smaller thing will be n squared over 4 all over e to the st. Okay? And then from here, all you need to do is solve for e to get your inequality. Let's look at what happens. I'm not going to work the details out, but it gives you exactly this. But let's take a look real quick. Okay, so this will be the end of the proof. So why does this work? solve for e. If I bring e over here, it has an st exponent on it, okay? As does this. So eventually I'm going to be taking the stth root of everything here. So I'm going to have, at the very end, and I'm going to have a 1/4 out front, because that's raised to the st here and going to be reduced to by the st. In fact, take the stth root immediately. Start off by doing that. Then bring e over. Then bring those guys over. This will have an stth root on it, as will this have an s over t. It'll be s plus t over s plus t, which turns into 1 over s and 1 over t if you do the arithmetic. And it'll be negative n to the 2 minus 1 over s, 1 over t, once you take the root. Okay, that's just a brief explanation of what happens there. If you do the arithmetic, you easily see that you get this. Okay, so what does that mean? As long as e satisfies this inequality, basically for n fixed, think of n fixed for a moment there, then this inequality holds. And if that inequality holds, it means that there are fewer st-free graphs with st's in them than there are total graphs. So there exists some graphs with no st. Okay? As long as e satisfies that, such a graph exists. That's exactly what this guy says. What's the maximum number of edges you have? Well, it's got to be bigger than this in order to make this e work. Okay? And so that's the end of the proof there.